So I think B was saying, me and B work for a software IT recruitment consultancy called IO Associates. And it's obviously good, especially nowadays, to have things done virtually just to keep, I guess, the technical community together, as it were. And so never before we've had so much reach in terms of reaching out to people that is outside our usual sort of southwest region. So I think so. The last few times we've had, listeners or attendees from the US and all over the globe actually, which is quite exciting for us. So so this week, this month, we're lucky to have Simon to do a talk for us. As you can see, Simon, would you like to say a few words just as a quick intro?
Yes. My name is Simon Ritter. I am currently the Deputy CTO of Azul Systems, and I have been working with Java for a long time. I actually joined Sun Microsystems back in February of 1996. I had to think about that for a moment. Basically around the time that JDK 1.0 was launched, and I followed Java all the way through Sun Microsystems until we got acquired by Oracle. I spent 5 years at Oracle, and then they decided they didn't need my services anymore, so I joined Azul pretty much 5 years ago. And so that's where I am now.
Brilliant, thank you. So as always, the format is relatively straightforward. So Simon's going to do his talk, and if you've got any questions, please do so in the chat box. Hopefully that's working now. I think it is working. So if you've got any questions, put it there. And Simon, I hope you don't mind. I'll just butt in whenever there's a question on the floor.
Makes sense.
Yeah, perfect. And just so we can still have that, I guess, that interactive element to what is usually what we expect from our normal meetup. And then afterwards we will. Afterwards we'll have I guess 10-15 minutes. Should anyone have any further questions for Simon? I guess without further ado, Simon, it's all yours.
Okay, great. Thank you very much. Yes, so let me just do that. Okay, so presentation is called Java at Speed, Building a Better JVM. And I noticed that I should have changed one specific thing on my slides, which is the date. So yes, it's not the 12th of August today. That was for a presentation I did a while ago, obviously. And the idea behind this presentation is to talk about how we at Azul can address some of the limitations, if you like, in terms of how the JVM performs. Now, please don't be worried. This is not going to be a sales or a marketing pitch. What I'm going to be doing is talking about the low-level technical details of how we look at what the JVM does, how it works, and then some of the changes that we've made in order to change the way that it performs, both from the point of view of latency and also from the point of view of the actual throughput. So when I actually put this presentation together, one of the things that I first started to do was look at, okay, so what do we actually mean by performance when we talk about the JVM specifically? Obviously, we know about applications, and when we're writing applications, we know about how we need to work on certain code in order to make things perform better. But when we look at the JVM specifically, what do we mean by performance? I came up with a graph, which was my ideal for how the JVM should work in terms of our applications. And so this is my idea of speed in the Java world. So my graph looks something like this. And it's not a very interesting graph, but it does represent what our ideal would be, which is that when the JVM starts up, we want 100% of the possible performance that it can give us, and we want to run at 100% of performance all the way through the lifetime of the application, and then we stop. Now, yes, clearly that's a very sort of trivial thing, and it's a very obvious thing. The reality, though, is that when we look at how the JVM works in a real application, it looks somewhat different to this. So it looks typically something like this. So we start off with application performance, or the JVM performance, which is quite slow, and then gradually over time it speeds up, and then we see certain dips in performance as it's warming up, and then we see certain dips in performance even when it's running at the optimum level of performance. So let's sort of dig into this in a bit more detail and try and understand what's actually happening so that we can think about how we could actually change that to make it more like the performance graph that we want in terms of the ideal. And the reality is that when a Java application starts up, what we're dealing with is bytecodes. This is one of the things that has been the big selling point, if you like, for Java right from the very beginning. Write once, run anywhere. You can take the same class file, you can take the same jar file, and you can run it on a JVM, whether it's on Linux running on an ARM processor, or whether it's Windows running on an Intel processor, it doesn't matter. And the way that we do that is through these bytecodes. Bytecodes are instructions for a virtual machine, hence the Java virtual machine. And the problem is that the way that the JVM works with bytecodes is that it has to take each bytecode as a virtual instruction and convert it into the necessary real instruction for whichever platform it's running on. And most of the time that's a fairly straightforward one-to-one mapping, but some of the instructions can be quite complex and they need quite a lot of work to do, method invocation and things like that. And the problem from interpreting point of view is that there's nothing that the JVM does in terms of remembering what it's done before. So literally every time the JVM encounters a bytecode, it does exactly the same thing. It converts it into an instruction or a set of instructions and executes them. Next time it sees the same bytecode, it does the same thing. So there's no optimizations going on there. And that leads to quite slow performance if you compare it to certainly native instruction, or if you compare it to what we could possibly get from the JVM. So the developers of Java, they came out with this idea originally of doing bytecodes and interpreting. And Java was criticized as being slow compared to C and C++. What they then did was they looked around, they said, okay, there are some better ways of doing this. And what we'll do is we'll use a thing called a JIT, a just-in-time compiler. And the way that JIT works is that essentially we keep track of how many times a particular method is called. And when that count reaches a certain threshold, we say, this particular method is a hotspot in terms of the code, hence the name of the JVM. And the JVM will say, because that's been executed a certain number of times, what we'll do is we'll rather than using the bytecodes from that, we'll convert it into native instructions, cache that, and then execute the native instructions every time we need to call that method. That's done with a thing called the C1 JIT. And the C1 JIT, sometimes referred to as the client JIT, is a very simple JIT compiler, which is designed to compile code as quickly as possible. But what it doesn't do is apply lots of optimizations. So it does very simple optimizing, but compiles the code very quickly. Having compiled it into native instructions, we then profile that as it runs. So that method we know is going to be called quite frequently, or is likely to be called quite frequently. As it's called in the future, we then profile that and collect information about how it actually executes and what it does. When the number of times that method is called reaches another threshold, we then say, okay, let's recompile it. And this time we'll use a different JIT compiler. So we use what's called the C2 JIT compiler, or sometimes referred to as the server JIT compiler. And that is a compiler which takes longer to compile the code, but applies lots more optimizations to get the code to be more effective, more efficient. And so that will then compile and we'll start running it again. And if we look at the graph here, we can see that the graph gradually increases in terms of performance. And that's as we go through finding all the methods which are going to be used frequently, and we compile them first with C1 and then with C2. But some of the things that we're seeing here are what are called de-optimizations. And that comes because of the way that some of the C2 compiled code works. C2 uses what are called speculative optimizations. And the idea behind a speculative optimization is that we look at how a piece of code has been used in the past, and we assume that it will be used in the same way in the future. Very simple example, if we have an if statement, and we look at the way that if statement has been used up until now, it's always gone through the true branch. of the if statement. We will assume that it will continue to always go through the if branch and will optimize based on that assumption. At some point in the future, maybe something strange happens and we have to go through the false branch of the code. So suddenly our code that we created is no longer valid. We have to throw it away. We have to then recompile it, and that's called a de-optimization. And that's not a very good thing because it obviously degrades performance. So we see dips in performance as we go through that. At some point, we're going to reach a steady state, which is where we've reached the maximum level that we can realistically achieve in terms of having compiled all the methods that are frequently used. We've used C1, we've then used C2, and we've eliminated all of the de-optimizations. So we've got a nice steady state in terms of our compiled code. But what we still see are dips in performance in terms of the ability to run our application. Those are due to something else. Those are due to garbage collection. And so we see garbage collection pauses that affect the optimum level of performance we can get. So the big challenges we like for the JVM is that we have a managed runtime environment, meaning this is really good because as developers, we don't have to do a lot of work that we would normally have to do in terms of C and C++. We don't have to deal with memory allocation. We don't have to deal with reclaiming space when we don't need it anymore. We don't have to deal with optimizing things in terms of performance and compilation and things like that. So we have a managed runtime environment. And the two things that are most sort of important in that respect are the garbage collector. And one of the things about the garbage collector is that it's inherently non-deterministic. And by that, I mean that we can't predict when it will run or how long it will take to do its work. You could make certain assumptions and you could try and predict based on how an application is running, but realistically, it is non-deterministic. And so we can't figure out, okay, every 20 milliseconds or every second or every minute, something's going to happen that will interfere with our application performance. The other thing about the garbage collector is that pause times can be really big. And I'm sure that if you've programmed in Java, if you've run applications, certainly in enterprise, you will have come across situations where garbage collection pauses could be hundreds of milliseconds, they could be seconds. If you're very unlucky, you could see minutes in terms of garbage collection pauses. The longest garbage collection pause I've come across is one customer that I was talking to in the US, and they had garbage collection pauses 1.5 days. And that's the sort of situation we go, well, okay, you've got a 1.5 day garbage collection pause. After a couple of hours, do you even realize that, has the application crashed? Is it still doing anything? And they said, no, we have JMX instrumentation. We know that garbage collection is still going on, so that's fine. And I remember saying to them, well, hang on, isn't it just easier to stop the JVM at that point and then restart it and avoid the whole garbage collection thing? And they said, no, it actually takes more than 1.5 days to load all of the data that we need and process it so it's ready to start the application. When I talked to them about eliminating garbage collection pauses, they were obviously a very happy customer. We'll kind of talk more about how we can do that in a moment. But yes, pause times can be very big. The second thing is the fact that we're dealing with bytecodes and not machine code. And the whole idea of JIT compilation and adaptive compilation, how we approach that, the strategies that are used, this can have a big impact in terms of performance, not just the overall performance, but how long it takes for that application to warm up, to get to its optimum level of performance. So these are the things that as Azul, we've tried to look at and say, how can we think about those in a different way and change the performance that we get from the JVM? So the question is, what if there was a better JVM? What we like to say is, well, there is, it's called Zing. So from a basic point of view, the Zing JVM, rather than starting from scratch and saying, okay, let's completely rewrite the JVM, let's start again, write everything new. We said, well, most of it works really well. So let's take the OpenJDK source code. It's open source, we can do that. And what we'll do is we'll change bits of it, the things that we think are worth changing. Most of it we can leave alone because it works very well, but there are certain bits that we need to modify to get better performance. The very important thing from our perspective and also our customers' perspective is that once we've made those changes and we've compiled the code into the binary that we provide for distribution, we run all of the TCK tests on that binary. And TCK is the Technology Compatibility Kit. It's part of the Java specification request through the Java community process that makes up the standard for Java. It's about 150,000 tests that give you a very high level of understanding that what you've got is a high level of confidence that the JVM that you're running will run your application code in exactly the same way as any other JVM that passes all of those tests. The important thing about that is it is a drop-in replacement for other JVMs. What that means is, as a developer, you don't have to think to yourself, okay, I'm going to use Zing, but I have to modify my code. I've got to recompile things. Don't have to do that. Take the same code, don't have to recompile it. You can use the same class files, same jar files, and so on, and everything will work in the same way. What we've done is to replace certain parts of the JVM. And specifically, we looked at garbage collection and we said, okay, let's take all the existing hotspot garbage collectors, Serial, Parallel, CMS, G1, Shenandoah, ZGC, all of those, and just remove them. And what we'll do is replace them with a single garbage collector that we call C4. And all of these things I'm going to talk through in a bit more detail as we go through. The other thing that we did is we said, well, okay, so the garbage collector is a very specific thing that works in terms of memory. And we looked below the JVM and we said, okay, on Linux, you have a virtual memory system. Virtual memory system will map from physical pages of memory to virtual address space used by a process. And it's very good in terms of what it does, but it's been designed for general purpose applications. With JVM, that's a very specific user of memory. And we said, okay, how about if we installed some kernel level code that sat alongside the virtual memory system of Linux? So other applications can continue to use the existing virtual memory system, but we'll replace that for our virtual machine, and we can then manage memory in a better way for the JVM. And that's what we call Zing system tools. So the reality of that means that we only support Zing on the Linux operating system. Technically, there's no reason we couldn't use Zing system tools on Windows. We could do it on Mac, but because of the resource constraints we have, we've targeted just Linux for that. More recently, what we've done is look at how we can improve JIT compilation. And to that end, we've replaced the C2 JIT compiler with something that we call Falcon. And again, I'll explain what we've done in terms of that in a moment. And then the last thing we've done is to add some additional technology to the JVM and the JDK, which we call ReadyNow. And what that's designed to do is, as far as possible, to minimize the time it takes to warm up your application, to go from the interpreted bytecodes through the C1 compile code to the C2 compile code and get your optimum level of performance. So we'll explore how that works later on as well. Talk a little bit more about the Zing system tools. As I said, this is the idea that we have better memory management between the operating system and the JVM itself. Some of the things we can do there are certainly being able to return memory more easily from the JVM to the kernel. And that means that if you're running multiple JVMs, what you don't want to do is tie up lots of memory in the heap of one JVM, even though it maybe is not using all of that memory, and then make it available to other JVMs as well. Other things we can do are things like making sure that, because we know the status of cache lines, we can say that if we've got a lot of allocation going on with a JVM and we've got thread local allocation blocks that need to be allocated, we can use our knowledge of what's going on at the kernel level to make sure that the pages we allocate to the JVM are hot, meaning that they're in cache and so they're more accessible. And then there are some other clever tricks we can do around things that, such as what we call contingency memory. Contingency memory is the idea that when we start up the operating system, we will actually grab a certain amount of memory and keep that for Zing. And that's just the way that we do it. What we do is we allow memory to be allocated from the operating system to the JVM, but we keep some of the memory in reserve. That's our contingency memory. If you've got an application that's running and you've allocated 8 gigabytes, for example, to the heap space, and you run your application and most of the time it's running quite happily, it keeps well within that 8 gigabyte limit. Then suddenly you come up against an unusual situation and the rate of allocation goes up and your heap usage goes all the way up to 8 gigabytes. At that point, if you try to allocate beyond 8 gigabytes of heap space, you get an out of memory error and your JVM will stop abruptly. If that's a mission critical application, that's really not a good thing. With Zing, if we have some contingency memory left, because it's not infinite, so we can't guarantee that, but if we've got some contingency memory left, when you get to your 8 gigabyte heap space limit and you try to allocate beyond that, we will then allow you to do that. So you can go beyond 8 gigabytes. At that point, we'll start running the garbage collector more frequently, trying to bring you back into the 8 gigabyte range, and we'll send you a set of messages, the log on the console saying, hang on, you've gone beyond 8 gigabytes. But it means that there's the opportunity to stop your application from causing an out of memory error and stopping abruptly. So it's sort of a useful thing if you kind of hit these odd situations.
Simon, I've got a question from
Sure.
Andrew.
Okay.
He's asked, will ZST be redeveloped for other operating systems? For example, a previous contractor had used the Azul JVM on a Windows machine for OpenGL rendering on a Windows machine.
Right now, we don't have any plans to move it to Windows. As I said, technically, there's no reason we can't do that. It's just simply that the resources we have, I mean, we are quite a small company, the resources that we have to be able to do that and then having to support it as well, it just isn't, when we look at the number of customers we have in terms of their usage, most people are using Linux on their servers, so it's just easier for us to focus on that. So unfortunately at the moment, no, we're not planning to move Zing or ZST to Windows.
Great, thank you. Hopefully that answers your question, Andrew.
Okay. Okay, so let's talk a little bit about garbage and garbage collection. As I said, there are a number of garbage collectors that are available in the hotspot VM. So you've got the parallel collector, CMS collector, G1, Shenandoah, ZGC. Shenandoah and ZGC, I'm saying here that they're research projects, not yet in production. Okay, JDK 15, they've now been made a production feature, but JDK 15 is not an LTS release. So we sort of move past those for a bit. Now, in terms of those options, all but one commercial garbage collector at some point will resort to a full compacting collection. And that's where you see these very long pauses, because the pause time is proportional to how big the heap is. It's not dependent on how much data you have there. The bigger your heap space that you've allocated, the longer those pauses are going to be. So when people were saying, 1.5 days, that's because they were using multiple terabytes of heap space. So what we've done is create this different collector, which we call C4. And C4 stands for the Continuous Concurrent Compacting Collector. Essentially, that tells you exactly what it does. The first thing is it is continuous, meaning that we will run at any time whilst your application is running. And we're continually looking at the heap space, determining whether we need to do some garbage collection work. Second thing is it's fully concurrent. We will do all of the work of the garbage collection whilst your application threads are still running. It's not like other ones, like if you look at CMS or G1, where certain phases are done concurrently, but certain phases or certain parts of those phases have to stop the world, stop your application threads, and then do their work. Everything we do is fully concurrent. Having said that, we are a compacting collector. Whilst your application threads are running, we will move objects around within the heap to eliminate fragmentation, to make objects contiguous in the heap. And it is obviously a collector. So that's why we call it C4, Continuous Concurrent Compacting Collector. From a basic design point of view, it is a generational collector. That means that we've divided the heap space into, in our case, two regions. We have the young and the old. And if you look at garbage collection design, you find that most garbage collectors use this approach. There is a thing called the weak generational hypothesis, and that says that most objects that you allocate in an application will only exist for a very, very short space of time. If you can collect them in the young generation and do that very easily, then you place a lesser load on the old generation. And so that's why we use two generations, so that we can eliminate a lot of garbage by doing young generation collections and not placing such a heavy load on the old generation. We do, however, unlike in Hotspot, use the same algorithm for both the young and the old generation. So it's a bit different. It is, as I said, fully concurrent. It's also parallel, meaning that each of those phases, we can apply a number of threads to the work that we need to do and not have to worry about that. So it's concurrent and parallel, and it's compacting. There is no stop the world compacting fallback. At no point will we ever give up and say, okay, we have to pause all your application threads, do a whole bunch of work, and then allow them to continue. So there is no case where that will actually happen. The algorithm we use is three phases. It's mark, relocate, and remap. Now, people obviously say, well, hang on, if you're going to start moving objects around within the heap, how can you do that safely so that I can make changes to an object and know that the changes I make will always be correct in the object, even though you're moving it around? The way we can do that is through what we call the loaded value barrier. Effectively, this is a read barrier, meaning that every time you access an object, we will intercept the reference to the object header, and we will do some work on that. We will use bits in the object header to determine certain things about what's going on, what the state of that object header is, and what phase of the garbage collection we're in. By doing that, we can enforce two rules on the object header that we give to the application code. First is that if we're in the marking phase, we guarantee that every object reference that you get will always be marked as in use. That way, we can avoid the problems of accidentally garbage collecting something which is being used and we've forgotten to do the marking because something happened in terms of the way that the application code worked. So we will guarantee that you always get a marked object. If we're in the process of doing either the remapping or the relocation phases, then we guarantee that you will get a reference which is correct, meaning that you can make a change to the data in the object and that change will not be lost because you're updating the object that has subsequently or has been moved, and so those changes get lost. This is how we can do concurrent marking and concurrent relocation. Having said that, a lot of people will then say to me, well, hang on, if you're going to intercept every read to an object, surely that's going to degrade performance because you're affecting every single read to a reference, and that's going to place a load on the system. And the answer to that is, well, yes and no. Yes, it does, because we intercept every access to an object header and we do a certain amount of work. So technically there is an overhead involved. But the way that that works is that by using bits in the object header, we can do a fairly simple test and jump. So that's two instructions on the Intel architecture. And if you look at what that equates to in terms of the actual processor itself, it's a single micro operation. Most of the time, we don't have to jump to the handler. So we're simply doing a test and not jumping. And so from a single micro operation, that's less than a nanosecond of overhead per reference. What we found is that if you look at the overhead, once you get beyond L1 cache and you start referencing L2, L3, or even main memory, the overhead of those memory accesses is going to be far, far bigger than the overhead of our test and jump. So realistically, unless you could write an application that only used data that was held in L1 cache, you really won't see any degradation in performance because we're using our loaded value barrier.
Simon, can I ask you a question?
Sure, you can, yes.
It's not from me, it's from Bruno. If the Zing GC is fully parallel, does that mean that for Java apps running on Kubernetes, we should allocate at least 2 cores?
Let's come back and discuss that a little bit later on. But bear that question in mind, but I'd like to address that a little bit later on.
Cool.
So there's a few things I want to talk about first, and then we can discuss why that's not a problem. But yes, we'll come back and talk about that.
Perfect, thank you.
Okay. Okay, so how does this actually work? So the first thing we need to do is marking phase. And this is quite similar to the way that other algorithms work in certain respects. So what we do is we initially start out by creating a root set. And a root set is essentially a list of all the objects that you can access directly from your application code. So we scan the stack, we look at all the registers, we look at all the static variables, and we build up a list of all the objects that you can directly access. Obviously, those objects are likely to have references to other objects, and those objects will reference other objects and so on. So what we need to do is we need to trace through from the root set to all the objects and create a graph of accessible data. To do that, we set our garbage collection threads working on the root set, and they will look at each object and they will set the bit in the object header to say that this is a live object and in use. We'll then trace from there to the other objects that object references and so on, and construct our graph, marking each object as we find it. Because the root set consists of obviously a set of objects, we can then apply a number of threads to that, and they're independent objects, so there's no problem of having different threads bumping into each other and needing to deal with the issues of locking and so on. So we can have multiple threads working on this, and it all works very efficiently. Now, as I said, your application threads will be running at the same time. It's concurrent. And at some point, you may have your application thread which needs to access an object. When the object is accessed, we do our test and jump. So we look at the object header, and in this case, we'll see, hang on, this object is not marked as being live data. Maybe it's part of the root set, we haven't got to it yet. And in this case, we jump to our handler, and the handler will then say, okay, we need to set the bit to indicate that object is in use. And effectively, what we're going to do is use the handler to do a very small amount of the garbage collection work in the context of the application thread. What we then need to do is trace any object references from that object to complete our graph. But we don't want to do that in the context of the application thread because that could delay the application. It's an unbounded task depending on how many objects are involved and so on. To get around that, we simply pass the object reference to the garbage collection threads, make it part of the root set, and let the garbage collection threads then follow the references from there for us, and we don't have to do it as part of our application. Obviously, when an application accesses another object, if that header hasn't got the bit set, it will then do the same thing in terms of jumping to the handler, setting the bit, and so on. So this enforces that first rule. It guarantees that every object you get in your application thread will be marked as live data. So no accidental garbage collection of objects that we're using. Then we come to the relocation phase. And essentially what we're doing here is saying, okay, we've got gaps between our data, and what we want to do is to relocate those objects so that they're contiguous in memory, eliminate any fragmentation. In the example I've got here, we've got 5 objects, A, B, C, D, E, spread out through our heap. What we want to do is figure out where we could copy them to so that we could make them contiguous in memory. And we can do that very simply because we can simply say, okay, let's make A prime, B prime, and so on. That is effectively compaction. We move them to different places in the heap and make them contiguous. Different algorithms use different approaches to how to do that. What we do is we use a side table. And a side table records the changes in terms of where we're going to relocate those objects to. So A has moved to A prime, B has moved to B prime, and so on. Obviously, to make that a safe operation, we will put a lock around the actual copy operation or move. And so when your application thread tries to access, let's say, object B, and we're in the process of copying it, it will be blocked because of our lock. Whilst that will introduce a very small pause to the application thread, it's not really going to be noticeable. Most objects are very, very small. They're only of the order of a few kilobytes, maybe tens of kilobytes. And so the time it takes to copy an object from one place to another is going to be very, very small. So the lock and therefore the blocking is also going to be very, very small as well. The other thing we can do is we can use the Zing system tools. And I mentioned the fact that because we control the mapping between the physical pages and the virtual pages, we can do some clever things. And this is one of the things that we can do. It's called quick release. Effectively, the idea is that we can collect an entire heap, whether up to 20 terabytes of heap space, with only one free page per garbage collection thread. So literally, if you've got, I don't know, 8 threads that you're using for garbage collection, you would only need 8 pages of free memory in order to be able to collect 20 terabytes of heap space. The reason we can do that is because we need one page that we can allocate to say that that's our starting point. So in this case, what we're going to do is we say, okay, we need to move some of our objects to a page. So we'll allocate our free page. You can see the red one there at the bottom. And so we'll copy objects to that page. But then in the case of the two on the left-hand side there, what we had as A and B, once we've copied those, we know, as the people who've developed the JVM, that those references will never be used again because of the fact that we will redirect things to the right place. So we can effectively steal the page from underneath the virtual address space. Now, you would never do this in normal operating system, virtual memory systems. But what we can do is we can say, okay, let's take that page, we'll steal it. Now we've got a free page of physical memory. Let's remap it to a different virtual page. And then we can use that to copy more objects to that free page. Even though those objects are still technically there on the top line, we're never going to use them again, so we can steal the physical page with the data in it. And similarly, once we've freed the next page, we can steal that and make it available. So this is hand over hand reclaiming of space and then being able to reuse it so that we can do the whole heap with only one free page per garbage collection thread that we're using to do that. Having done the relocation, we then need to do the remapping phase. So essentially what happens here is that we've got our side table, and that was actually one of the points where we need the side table, is because we're going to steal the page. Other algorithms use a thing called a Brooks forwarding pointer, which is part of the object itself. So by not having the change in reference recorded in the object itself, we know we've got the side table and therefore we can do that. So we come to the remapping phase, and now what we need to do is update all of the object headers to reflect the fact that they have been moved to somewhere else. At that point, what we do is we start our garbage collection threads working again, and they will read from the side table, and they'll say, okay, A has been moved to A prime. Let's update the reference in that object header, and then set the bit to indicate that that object has been updated. We can do that in parallel, again, because we don't have any issues of bumping into each other and things like that. However, our application threads are still running. So at some point, the application thread is going to access an object and we'll find, oh, hang on, the bit hasn't been set to indicate that that object has been updated. At that point, again, we jump to our handler, and within the context of the application thread, we'll access the side table, take the address, update it in the object header, set the bit so we don't have to do it again, and then return that to the application thread so we know we've got the exact value of where that object is located, so we can make our changes and we don't have any inconsistencies in terms of the data. So the algorithm is fully consistent, no problems with running into any issues. So what this allows us to do is to scale up to very big heaps. So I mentioned the fact we can scale all the way up to 20 terabytes of heap, and you won't see any degradation in terms of pause times. So literally you'll see the same pause times whether you're using half a gigabyte of heap or 20 terabytes of heap. We do use this approach. One of the things that our customers like is that often, because of the proportionality they see with other collectors in terms of the time it takes to do the garbage collection, they basically separate out their data into multiple small heaps. Now with Zing, they can actually use one big heap. Makes life easier because you don't have to divide things, you don't have to code against that. And so it's a whole different approach, makes life simpler. The other thing to really say is that Zing, although it does work with very big heaps, it doesn't actually require big heaps. So yes, big heaps are good, but you don't actually have to have a big heap to make it work. You can go all the way down to half a gigabyte and there's no problem at all. Now, let's talk a bit about GC tuning, because what we find a lot when we talk to people who are trying to minimize the latency of garbage collection is they spend a lot of time and effort simply trying to change the parameters they use on their VM to try and get rid of the problem of garbage collection. And the reason that they do this is because there's lots and lots of options that they can change on the command line that affect how the garbage collector works. There's literally hundreds of options you can set on the command line that will change which garbage collector you're using or certain parameters of that garbage collector and so on. I'm sure if you've done any sort of Java deployments in big systems, you know about all the different things that you can change. And here's two examples. And these are two examples taken from real customers that we've worked with in the past. And I don't want to talk through all the different options that they've used here, but I'm just going to highlight one particular thing where they have both set the survivor ratio of their heap space. Survivor ratio is within the young generation, you've got Eden space and then you've got two survivor spaces, and survivor ratio basically sets how big the Eden space is compared to the survivor spaces. Okay, now in this first example, they set the survivor ratio to be 128. Second example, they set the survivor ratio to be 2. The question is, well, what's the right answer? Is it 2? Is it 128? Is it 64? Is it 17? Well, probably not 17 because 17 is not an even number. But you get the point, which is that there's no easy way of saying, well, just set the survivor ratio to be this and everything will work really well. And what we find is a lot of customers end up spending a lot of time trying to trial and error, saying, okay, let's set it to 2, let's set it to 128, then let's set it to 64, monitor the performance, see which one gives the best result. Now, if you only have one parameter to change, that wouldn't be too bad. But there's lots of parameters you can change. And so you end up with an n-dimensional space that you're trying to solve for the best solution. Very, very difficult. Okay, so that's hotspot. How would the same set of parameters look for Zing? It's actually quite simple. It's that. What we do is we basically set the heap size, and that's it. To start with, all we do, set the heap size. Now, yes, we do have a few parameters. There's probably, I think last time I looked, I think we had about 7 or 8 parameters that you could set in addition to that. But most of the time, we don't actually need them. So all we do is we say, right, set the heap size and let the algorithm do what it does and make it work. And typically, tuning, all that involves is trying to find the right size for the heap space. So you start off with like a big value, make sure your application runs, then you turn it down. Okay, so you get the same level of performance you're happy with, and then you just kind of turn it up a bit to give you some headroom so that if there's an additional load, you can still deal with that. And that's really all you have to do to start with. Next thing, how can we actually show that what we're doing works? How can we actually prove to you that what we're delivering really solves the problem of garbage collection? So we wrote this thing called JHiccup, and JHiccup is designed to monitor the latency of the JVM and everything below it. So we're not looking at latency associated with your application, because that would depend on what your application is actually doing. So we just want to look at what's the impact of the JVM and the operating system and the hardware on your application. To do that, we run a thread alongside your application in the same JVM. But to avoid the problems of Heisenberg's uncertainty principle, the act of observing something changes it, what we do is we say, let's have that thread spend most of its time asleep. So it doesn't interfere with the performance of your application. When the application starts up, we go to sleep for 1 millisecond. When we wake up, we look at the system clock using nanosecond resolution, and we say, we expected to wake up at this time. What time did we actually wake up, and what's the difference? So, for example, if we go to sleep and we're running on hotspot, there's a 20 millisecond garbage collection pause. When we wake up, we can record the fact that there was a 20 millisecond delay on when we expected to wake up and when we really woke up, and then we can record that and create some nice histogram log files, which we can then graph. If we look at some results, so here's an example of a system that we tested. This was running Elasticsearch on a 128 gigabyte heap. And what we've done here is we've graphed on the left hotspot, and on the right we've graphed Zing. What we're seeing here is the latency in terms of the time for both hotspot and Zing that will affect your application. So it's not the application code, remember, it's just the JVM itself. If we look at the left-hand side, what we see is a very typical kind of graph that we would expect from hotspot, because you're seeing lots of small spikes, and those represent minor GC pauses, garbage collection of the young generation. And then there's two bigger spikes, which represent longer pauses associated with garbage collection of the old generation, major GC. Very typical kind of graph. We've run both of these on identical machines. So we took the same machine, ran it on hotspot, ran it on Zing. So all we had to do was change basically Java home and run the same application with the same workload and gather the results. Now, if we look at the right-hand side and we look at Zing, what you see there is a much more sort of random looking graph. And because high is bad, you might look at that and go, well, hang on, that really doesn't look very good. You know, so the hotspot's kind of quite low most of the time. You've got two big spikes, but on the right-hand side, you've got lots of sort of random noise and several big spikes. But I have been deliberately misleading here because I have used different scales on the graph. So on the hotspot graph, I've gone from 0 to 8 seconds, meaning that most of those minor GC pauses are around half a second. The two major GC pauses are somewhere around 5.3, 6.2 seconds. The Zing graph, I have scaled from 0 to 80 milliseconds, meaning that the big spikes are somewhere around 50 milliseconds, and I think the biggest one there is about 65 milliseconds. If we scale those graphs using the same scale, then we see the real effect of Zing. Because you can see here that suddenly you've gone from having these spikes associated with garbage collection to suddenly, boom, nothing. You have to change the scale of the graph to understand what's going on. Now, if we went back and looked at that earlier graph, the previous slide, some of that effect is from the operating system and the hardware. So you'll see context switching in terms of the OS that will affect it. But from a GC point of view, there's essentially nothing happening that will affect the latency of your application. So you're moving from the left-hand side where you do see effects of garbage collection, right-hand side, no effects of garbage collection.
Simon, can I ask you a question?
Sure, you can, yes.
Brilliant. It's from Darren. Hi, Darren. Hope you're doing all right. So he's asked, does Azul Zing GC also have a finalizer thread for running finalized methods?
Mm-hmm.
Sometimes third-party libraries have had those methods.
Yes. Yes. So, I mean, obviously, finalization is one of those nasty things, and it does have an impact in terms of when you can garbage collect an object. Now, obviously, we're still bound by the same constraints in terms of the way that the JVM has been defined, meaning that if you have a finalizer method, if you have a finalizer method within your class that needs to be called, then we have to put it on the finalizer queue, and therefore we have to execute the finalizer method and so on. So yes, that would have some impact, but we try to minimize that as far as possible in terms of running the finalizer thread as quickly as possible. But yes, unfortunately, there's nothing we can do because of the definition of the JVM to prevent finalizer methods from being run if they are necessary. One of the things that always when talking to people is basically, well, you try not to use finalizer methods. That's basically the advice for that.
Darren said he's had issues with GC on the finalizer thread as low priority task.
Yeah, like I say, we try to keep that as high priority as possible, but like I say, unfortunately, we are bound by the way that the JVM has been defined, so we do have to run finalizer methods before we can garbage collect objects.
Cool, perfect. Thank you. Cheers,
Okay.
Simon.
As I said, you do not need to run with a large heap. So that was 128 gigabytes of heap. Let's look at a similar example. This is running Hazelcast with a 1 gigabyte heap. And what we can see here is effectively the same sort of result. If we were running on hotspot, we would see sort of a big spike up in sort of 230 milliseconds. And then for whatever reason, this system really wasn't very well designed because you're getting almost continuous GC pauses in the mined GCs, somewhere in the 25 to 40 milliseconds. And again, you'd have to change the scale on the graph on the right-hand side to actually see any results from that. Okay, so that was garbage collection. Now let's talk about what we can do with the JIT compiler. And one of the things we said was, okay, if we want to change JIT compilation, what's the thing that we can do? And we looked at C1, and because it's designed with the idea of fast compilation, low optimization, what you don't want to do is really apply any effort there. C2 is where you're going to get the most improvement in performance. So you want the best optimized code that you can generate. So we looked around, and again, we said, let's not start from scratch. Let's find out what else is available. And we found there's this really good project called LLVM, open source project. Lots of companies contribute to that. There's people like NVIDIA, there's people like Intel, Microsoft, Sony, Apple, all sorts of companies that understand about hardware, understand about compilers, how to write those kind of code, have contributed to this project. And so we said, okay, this is a project which is primarily aimed at developing the back end of static compilers. So you take intermediate representation generated by your front end, and then you optimize it and generate the instructions for your particular architecture so you can run your application. So we said, okay, can we take that and integrate it into the JVM and make it work as a JIT compiler rather than a static compiler? And that's what we did. So we took all this code, we integrated it with the JVM, made it work with the garbage collector and all those things, and then contributed that code back to LLVM so other people could do that if they wanted to as well. What this allows us to do is get better performance in terms of the code that's generated as part of the C2 or the Falcon compilation process. Better use of intrinsics, more inlining, fewer compiler excludes, all of which add up to better performance. Now, to give you an example, if we look at something as simple as this is a piece of Java code that just takes an array of integers and then adds them up. Hand that to any modern compiler and it will say, aha, this is something that we can use vector operations for. Vector operations have been around for quite a while. Used to be SSE on Intel, now it's AVX, AVX2, AVX 512. Essentially, a vector operation is where you have a very wide register and you load up multiple elements from your array, and then you apply a single operation to them as one clock cycle. That's single instruction, multiple data, been around for a long time, works very well. As I said, take this piece of code, give it to a compiler, and it will say, yes, we'll use vector operations where applicable. However, if we make that even a little bit more complicated, and we start introducing the idea of a conditional, and we say, okay, we've got two arrays, and we want to add them together, but only if the second one's even, then we have a more complex situation. If you give that to C2, it will not be able to recognize that as something which can use vector operations. In the case of Falcon, it will. And so it will still apply the same optimizations that you would get for the previous piece of code. Again, so I kind of put that into context. If we look at that piece of code and we look at the output of C2, this is typically what you'd see. Now, don't worry about all the instructions that are going on here, but the red boxes represent what the compiler has done is it said, okay, we've got a loop here, we want to optimize it, what can we do? And it does loop unrolling, effectively saying rather than doing the same number of iterations you've got defined there, we can see that we don't need to do that, so we'll do 2 elements per iteration of the loop and improve performance very, very slightly. If we look at the same code with Falcon, it looks very different, and the red box is actually bigger to start with. But what's going on here is that we're actually using vector operations. So as I said, we can take advantage of that. And so now, because the particular processor we're running on here has AVX2, meaning it's a 256-bit wide register, and there's more loop unrolling going on, we've actually managed to recognize that we can do 4 elements per loop, plus the use of the vector instructions. We get 32 elements per iteration of the loop, rather than the 2 that we got with C2. What that equates to is much better performing code in the case here where we've got numerically intensive operations. Now, that's just one example of some of the things that we can do with Falcon. There's lots of other things we can do. Falcon is a much more modular design, meaning that it's very easy to add things to it and new optimizations and so on. And the great thing that we as a company can take advantage of, it's an open source project. All these other people are contributing things. We just do a rebase off the open source project, and suddenly we can pick up other things that people have done in terms of improving the code. So this is a great example of how we can pick up performance improvements. Last thing I want to talk about is ReadyNow as a way of eliminating warm-up time. And so as we saw, we go through this process of interpreted bytecodes, C1 compiled code, collecting profiling information, C2 or Falcon compiled code, de-optimizations where speculative optimizations don't work, so on and so forth. The next time you start the application, you do the same thing all over again, which doesn't really make any sense if you've got an application that you want to restart with the same workload and the same kind of setup. What we do with ReadyNow is we say, okay, let your application run, start it up, get it running to the optimum level of performance, and then we'll record a profile. And the profile records 4 pieces of information. First is all the classes that are currently loaded. Second is all the classes that are currently initialized, and that could be a subset of the ones that are loaded. Then we record all the instruction profiling data that was collected as part of the C1 compiled code and the profiling information before we fed it to Falcon. And then most importantly, we record all the speculative optimizations that failed. So where we made an assumption about how the code was running, that assumption had been wrong, so we'd had to throw away the code and then recompile it. What we can then do is collect that data over a much longer period of time. So we can say, okay, sure, you might wait a minute, 2 minutes, but you could wait a day, you could wait a week until your application is really, really warmed up and everything is running just the way you want it to be, and then collect the information. What it does is allow us to give the JVM advanced information about how that code has been running and avoid a lot of problems with de-optimizations. Speculative optimizations we found give us about 50% of the improvement in performance. Where we can avoid those de-optimizations, that's a really big win in terms of the warm-up time. How we use that is essentially to say, when we start up the JVM, we know the application we're running, okay, so we've got now our profile, let's load all the classes that we can load straight away, let's initialize all the classes we can initialize, use the profiling data and the speculative optimization failure information, and compile the code straight away that we need to run that application. Do all of that before we get to main. Literally, when the application enters the main entry point, you'll be running with codes about 98% of the performance you had when you took the profile. What we found is that typically you need about 1, 2, maybe 3 transactions to just kind of kickstart that application into the same level of performance you had when the profile was taken. So that's a much shorter warm-up cycle than you would have normally. And in fact, if you look at a graph here, again, sort of taking information that we collect from our JHiccup profile, what we see is that with the orange graph, you're looking at application that is not using ReadyNow. So it starts off slow. This is latency, remember. So it starts off slow, gradually goes through compilation, de-optimizations, recompilation, so on, and then gets to a steady level of performance. With ReadyNow, the blue line, we start off really low because we've compiled all the code that we need, and therefore we're running with native instructions rather than having to go through all the same process every time. Now, one of the things that we have to look at is the way that the graph is shaped. So if we generalize the first graph that I showed you, without ReadyNow, you have a warm-up time where we gradually go through the same process before we get to our optimum level of performance. With ReadyNow, it's a different shaped graph. But the problem we get is, even though we've got a nice steep graph in terms of our performance profile, we've got this bit at the beginning, which is where the application's not doing anything at all. And that's because we have to do this class loading, we have to do the class initialization, and we have to do all this compilation before we can run the main application. And we looked at that and we said, "Whoa, that's okay if you're running like a trading system, and you can say, okay, well, our trading starts at 9 o'clock, so let's run our application at 5 to 9, gives it time to do the class loading, initialization, compilation, and everything." But if you're running on things like microservices or stuff like that, then you really don't want that kind of blank period where nothing's happening. So we looked in more detail about what was going on inside the compiler. We said, okay, well, we've got our bytecodes, and we translate those into the intermediate representation used by LLVM, and we pass that to LLVM to compile. To make the optimizations work, the compiler actually uses callbacks to the virtual machine with a set of queries to understand how that code has been used. So this is where we take the profiling information and we can use it to understand how to optimize the code with the compiler. So we send a set of queries to the virtual machine, we get a set of responses about how it was used. That then allows us to generate the code, get our compile method, and then we can execute it. Okay, that's the way it works.
Simon, can I butt in?
Sure. Yes.
We've got a question from Alan. Can we dynamically save and load different profiles for, say, completely different mathematical processes that an application may or may not perform?
Absolutely you can, because you see a profile is just a profile. So when you collected it is irrelevant to when you start the application up again, which is one of the advantages of this, because you can collect a profile on Monday morning because you've got a Monday morning load. You collect a profile on Friday afternoon because you've got a Friday afternoon load. And then, as you say, you've got different mathematical loads on your system. So you use different profiles. When you restart the application, you can select which profile to use in order to get the performance that you need for that particular load that you know that you're actually running with. So yes, it's completely flexible. The profile information that's collected, it's actually a text file. You can just read it, have a look at it, and see what's collected in there. There's lots of kind of random stuff that you wouldn't really understand in great detail, but it is a text file, and so you can load whichever text file you want when you start up the application.
Perfect, thank you.
Okay. So the other thing that we found was that LLVM is fully deterministic. And that means that if we take the set of information here, so we've got a method that we want to compile, and we've got our initial intermediate representation, which we generate from the bytecodes of the method. Clearly, if you recompile the method, you make changes, then we can't use the same profile because things have changed. But assuming you haven't recompiled your method, you've still got the same bytecodes, and you have the same set of profiling information. When the compiler uses the queries and responses from the VM, what we've got is essentially the same identical set of inputs. And we know, because the compiler is deterministic, that given identical set of inputs, the machine code that we generate will be guaranteed identical as an output. We can take advantage of that. So what we now do is called compile stashing. And compile stashing says, right, in addition to recording the profile with those 4 pieces of information, let's also take a copy of all the code that was generated by the JIT compiler as part of the warm-up process and got us to the point where we're taking that profile. That's our compile stash. That we can use as effectively a cache between the JVM and LLVM. When we start the application up, we've got our information about what methods we want to compile. We've got the information about the various different profiling information and so on. So we can effectively use the compile stash. So if we know that the inputs match, then we know the outputs will match. So we can avoid using the compiler and simply take the code directly from our cache, from our stash, and avoid the overhead of compilation.
Simon?
Yep.
Is there any way to convert all the code to native code rather than load what has been loaded before JIT? And also, can it also do selective swapping of classes if some classes have been replaced with new developer code?
Right. So the first thing is, no, you definitely don't want to do. So this is basically the difference between ahead of time static compilation and using JIT compilation. Because you could say, okay, well, let's just compile all the code in our application. But it's the 80-20 rule. 80% of the time, you're only using 20% of the code. So it doesn't make sense to compile everything because there's a lot of code in any complex application that will never be used for most runs. So it's a waste of time to compile it all and then try and reuse it. So what we do is we focus on the code that actually makes a difference from the point of view of performance. The second bit about dynamically using different classes, right now we don't do that. I know we are sort of investigating that. We actually have a big project that we're working on specifically around that. But at the moment, the way that ReadyNow and compile stashing works is it is very much with a fixed profile. So if you recompile code or you change the classes that you're using, then that would invalidate the profile and we can't then do that. But there is some work that we're doing to work around that. So that's what I would say to that. Okay, so as I said, without compile stashing, we have this kind of period of time before the application actually starts doing any useful work, and we want to minimize that as far as possible. And with compile stashing, we can effectively shift that over to the left and minimize that blank bit of time. And by doing compile stashing, we can reduce the compile time by up to 80% and reduce the CPU load, because of course compilation takes a lot of effort, by up to 60%. So that is really shifting the graph in the way that we want it to be. Just to summarize then, essentially what we're saying with Zing is we're going with the idea of start fast, go faster, and stay fast. And then what we want is obviously a simple replacement for other JVMs so that we don't have to worry about recompiling our code, we don't have to change our code. One of the things I didn't mention is that since last year, we now don't have to use ZST. You still can if you want to. For very large heaps, you have to. But for smaller heaps, less than a terabyte, you don't have to use ZST. We have some a variation where we use some different Linux system calls so that you can avoid having to use ZST. And if you're deploying into a container, for example, then you just have the Zing JVM. No worries about installing other things in the host operating system or anything like that. Now, there was a question earlier on about the number of threads, wasn't it? As well, like the parallel nature of things. And I did say I'd come back to that. And this is where, obviously, because we're doing garbage collection concurrently with application threads, if you had for example, if you had a small number of threads, let's say you've got 4 cores that you're using for your application, suddenly you want one of those has to be used for garbage collection, then what you're going to find is that your throughput will drop by 25% because suddenly you haven't got the 4 cores that you need to use for your work because one of them is being used for GC concurrently. So the advantage, again, of using Falcon is that because we've been able to raise the level of performance of the throughput of your application, that the effect of having concurrent garbage collection is pretty much eliminated. So you will get this over, I can't guarantee it, but overall you'll get very close to the same level of throughput you would have had before, but without the pauses associated with garbage collection. If you're interested in this, we do have a free trial. So there's a 30-day free trial. Go to azul.com/Zing trial. You can download Zing, install it on your machine, have a go. If you want some help, one of our SEs will provide you with some assistance in terms of producing these nice graphs and showing to your boss and going, look, this is the thing that we can do, and we can solve the problem of latency in our application. So that is pretty much it for the presentation. So I don't know if people have any more questions. I'm very happy to take those.
Simon, I've actually got a question from Yaz. Although he sent it to me privately. So Yaz, I hope you don't mind me just saying it word for word, mate. Unless you want to ask the question yourself.
Yeah, okay. I wasn't sure how to kind of articulate it because I'm just an amateur Java developer. I'm a Scrum Master, all of that kind of lovely stuff. But I like to kind of keep involved and understand what's going on and what have you. But the garbage collection stuff, I understand that, and that's great. It's great for performance, making sure that you optimize how you use that interaction between your application and the operating system and the actual machine that you're operating on. The compiler stuff, I didn't quite understand the benefits it gives you, because most sort of enterprise type applications, they're not meant to be switched on and off, and I can only see that the benefit of that being, if something is switched on, switched off, and then switched on again.
Okay, so there's two parts to it. So the ReadyNow bit is the one where we can reduce the warm up time. So that's where, yes, if you turn it on, you turn it off, turn it on, turn it off, that gives you the advantage. But the Falcon JIT compilation is because the effective level of performance you get when it is warmed up is higher. So that actually works really well with enterprise applications, with long running applications, because we can give you higher overall performance than you would get with C2, because we can apply more optimizations, we can do more tricks underneath the covers with the code that we generate. So the two sort of distinct things. One is Falcon, which is about long running applications, better overall performance. And then ReadyNow is if you want to restart applications like microservices, spin them up frequently, then that's the thing that will help you with that.
So the profiling files that you were talking about,
yeah,
is that a Falcon thing, or is that something else?
Again, no, that's more ReadyNow. So ReadyNow is simply saying, okay, let's record information about an application that has warmed up, right, and then reuse it when we start the application. You could do it. We used to do it with C2. Right. Now we do it with Falcon because we've switched. So it doesn't actually require Falcon to work.
And the selection of those profiles, is that a manual thing, or
yeah. It's just a command line. You just say, okay, I want to start my application. Here's the file that I collected earlier, and just run with that file, and off you go.
It can't be done sort of dynamically or anything like that.
Well, yeah, I mean, dynamically in that you could have a script where you could say, okay, choose a particular file based on when you wanted to do that.
So you can't hot swap those?
Oh, no, you can't do it dynamically at runtime, no, because it's used when you actually start the application.
Yeah, so sorry if I didn't sort of...
No, that's fine.
All right, that was it.
Thanks, mate. Alan Stas, are embedded systems supported?
No. I would say that's because we only support Linux on Intel. So we don't have, for example, Linux on ARM, which would be a typical embedded application. I guess we could say yes, if you had an embedded system that was running Linux on an Intel processor and you had at least 0.5 gigabyte of memory. So not a Raspberry Pi, but if you found some of the Intel development boards, then yes, technically we could run in an embedded environment, but it's not really what it's targeted at.
Cool, perfect. Another question is there any sort of free or discounted offerings of Zing JVM for open source or non-profit projects?
Absolutely, there is. Yes, I'm happy to say, yeah. If you have an open source project and you're interested in testing with Zing or using Zing, then yes, please do contact us, and we do grant a lot of free licenses to people who are working on open source projects. So definitely, yes.
Love that. Thank you. Very generous. Question from Darren. What's on the roadmap for the next 12 months that you can mention?
Yeah, I mean, the thing that we're looking at the moment is like I said, is trying to figure out how to be more dynamic in terms of the compilation. And so we're definitely looking at ideas of how to improve that more from a cloud perspective. So almost like compiler as a service, so that you don't have to do all the compilation on the machine where you're actually running your application. So we could kind of outsource that, and just trying to detach the compilation part from the application. So that's kind of what we're working on at the moment. It's just being more dynamic in that respect. I think that's about as far as my boss would let me say anything.
Brilliant. Thank you. Distributed JVMs?
Yeah, I guess it depends on what you mean by distributed JVMs. I mean, yeah, you can distribute JVMs. Yes, you can use RMI. You could use different, RESTful web services to communicate between JVMs. So that's not an issue. As I said, Zing will work quite happily in containers, so you could do it in that model if you wanted to as well. So I guess it would depend on what exactly you mean by distributed.
He's either typing furiously or unless you want to unmute yourself, Darren. Yeah, I think that's it from him.
Okay.
Any other questions? Anyone else? Cool. I think that's it.
Okay.
But yeah, no, thanks. That was really good. I know B was gutted because I think she's recently got a new laptop, and I think her internet is slightly playing up. But what she has done is she's recorded me a message just so I can play to everyone.
I do see a question there, which is how often are releases?
Okay.
So I will answer that one because that's quite important. So what we're doing is we're basically following the same kind of long-term support strategy that everybody else is with JDKs at the moment, which means that we have Zing for JDK 8, we have Zing for JDK 11, and the next one will be Zing for JDK 17, although I think we are talking about maybe doing a Zing for JDK 15. But we're not following the 6-month release cycle with Zing because it's just too much effort on our part, and also our customers are not looking for a new Zing every 6 months. So yeah.
Perfect. Thank you. So I'll play this message from B. This kind of looks like that I'm broadcasting live from somewhere else. So I'll just play it. Hopefully everyone can hear it.
Hello everyone, thank you very much for joining us this evening. Apologies for not being very present, and also for having the connection difficulties. I hope Ines has looked after you all really well. And yeah, fingers crossed that sooner rather than later we can be sort of back in reality, and the connection issues then won't be a thing. We can return to pizza and beers then, as opposed to I've had some mango and pineapple and yogurt whilst watching this evening. Simon, thank you very much for your talk. Really interesting. Really enjoyed it. The video will be up online on the IO Associates website and LinkedIn as well, so just keep an eye. Just thank you very much for joining us. Speak to you all soon.
Brilliant. So as B said, I think usually it takes about 24 to 48 hours for the video to be accessible. But once that is, I will email everyone just so you have access to it. I guess if you don't have any questions, thanks a lot, Simon, once again. It was brilliant. And I'm pretty sure if we've got any sort of further questions, they'll reach out to me to reach out to you or reach out to you directly.
Yeah, I mean, either through you or, reach out to me on Twitter. I've got DMs open, so if anyone wants to ping me on Twitter, they can do that. One more question there.
One more question, yeah.
What's the question? Oh, do you have any technical blog? Yeah, we do. On Azul.com, I write a blog somewhat periodically. I should try and do it more often, but there's many things to do. And then we have another site that we're actually working on at the moment, which would be of interest, I'm sure, to everybody here, which is called foojay.io. So it's FOOJAY, which is kind of short for Friends of OpenJDK. foojay.io, there you go. Yeah, thank you. And that's a vendor neutral, lots of really useful Java information on there about all sorts of different releases. It's about OpenJDK. It's not about Zing. It's not about Zulu. It's not about any of our commercial products. It's about pure Java. Lots of really useful information there, but also lots of blogs on there as well. So feel free to have a look at that as well.
Cool, thank you very much. Darren's got one more question. Do you recommend any Java monitoring tools like AppDynamics, etc.?
Yeah, I mean, the ones that I've used mostly are like Visual VM and Flight Recorder and Mission Control, just because they're the easiest available. I don't have to pay for them. So those are the ones I tend to use.
Cool, perfect. Yeah, just saying whether there's anything else, but no, I think that's it for the evening. Again, Simon, thanks. That was great. And yeah, we'll follow up with a video when that's once that's also edited, etc. But yeah, thank you everyone for coming. Have a good evening, and best to go to the pub before 10 o'clock.
Yes, thank you everybody for listening, and I hope at some point we'll be able to meet up physically and actually have a jug meeting and actually meet up. But okay, thank you very much.
Great, thank you. Thanks everyone. Have a good evening.
Bye bye.
Bye.